Let us define the weight of a binary string as the difference between the number of occurrences of the 0, 1 substrings and the number of occurrences of the 1, 0 substrings. Consider that you have a tree where each vertex has either 0 or 1 written on it. Then, if you consider any path that starts from the root and goes down till the leaf, you will have a binary string that will have some weight. Then the score of this tree is defined to be equal to the sum of weight of all the binary strings that can be created along each of these leaves. However, the initial tree does not have just 1 and 0 on its vertices. It also has some question mark on the vertices, meaning that this value can be altered to be either 0 or 1. Now, suppose Alice and Bob are playing a game on this tree, and in one round, the current player can pick any of this question mark and replace it with either 0 or 1. Alice's goal is to maximize the final score of the tree after all the question marks have been replaced, and Bob's goal is to minimize it. Assuming that both the players play optimally, can you figure out the final score of the tree? This is the problem statement. Feel free to pause this video, read through the problem description, and try to come up with a solution before watching the rest of the video. Before solving this problem on a tree, let us first try to solve it on an array. After all, an array is also a tree. And while we are looking at the array version, let us look at the simplest case when there are no question marks present in the array. In that case, the weight of this string is already fixed. But do we really understand how to compute the weight of a fixed binary string? To do that, let us club all the identical elements that appear together into one single group, and we color it blue if the group represents a 0 block, and if it represents a 1 block, we color it green. Then it is quite clear that elements from the same group will never contribute to the answer, because the answer can only change when a substring 0, 1 or 1, 0 appears. So since their count does not matter, let us compress all of these elements into one single element and repeat it for every color that follows. Then the final string will look like an alternating sequence of colors. And now you can notice that every time there is a color change from blue to green, the score increases by 1. And every time there is a color change from green to blue, it decreases by 1. And it has now become clear that the final score will either be 0 or 1 depending upon the parity of the number of groups or the number of colors that you have just created by compressing these blocks. And if you want to dive more into the details, you can see that if the number of groups is even, then the final weight will always be 1. And since that is the maximum weight that is possible, Alice will always try to ensure that the number of groups is even. That is, she will always try to make sure that there are an even number of alternating blocks. We have established that whoever controls the parity of the number of groups is the winner of the game. So now let us look at the next simplest case when there is just one single question mark in the entire array. Then that question mark can either be on a terminal position or it can be sandwiched between two elements that are either identical or they are different. So now let us see if it is possible to manipulate the parity of the number of groups from this position and this position. So if this question mark did not exist, the string would have been equal to green comma green with the parity equal to 1 because there is just one green block. Now if you insert a 1 over here, the number of block stays same. It is just one green block. But if you insert a 0 over here, then the parity would remain same because the number of blocks is now 3. Green, blue, green. So it is not possible to change the parity of this configuration if you insert a question mark in between, no matter what you do with that question mark. What about this position? This is even simpler. If you color it with blue, it will get sucked in into this blue block, and if you color it green, it will get sucked in into this green block. Therefore the number of groups from this position was 2, and even after inserting this question mark in between, regardless of its color, the number of groups does not change. So now we have our breakthrough, that is, if you have just one single question mark in a non-terminal position, it is not possible to change the parity of the string. Now, what about the case when there are two question marks in the array? If they are not together, then from the previous slide we already know that neither of them can alter the parity of the number of groups. So the only case that we need to analyze is what happens when these two question marks are clubbed together and are sandwiched between either identical elements or distinct elements. At this point, of course, you can do some case analysis on paper and conclude that the parity of both of these configurations will never change. But I want to show you a very cool argument to arrive at that conclusion. Notice that if you have two question marks over here, then it must mean that you started with this initial configuration with no question mark, and in round 1 you must have inserted one question mark, and in round 2 you must have inserted the other question mark. But in the previous slide we have already discussed that whenever you insert a question mark between two elements, their parity will not change, and if you repeat this process, their parity will never change. So therefore if the parity is G, it remains G over here, and it remains G over here as well. Why does it remain G from here to here? Because from round 1 to round 2, this question mark is locked down. If it is locked down, then you are only inserting the new question mark between two known elements, and that means that it is identical to the first case that we discussed in the previous slide. Therefore the parity will never change no matter how many question marks you have, and the argument is that you can build this string from ground up every time inserting one question mark, and we already know that every insertion never affects the parity of the number of groups. We know that insertion between any two elements never affects the parity of the initial configuration. Therefore, no matter the number of question marks in between, the parity of the number of groups of the initial configuration, which is green comma green, will always remain the same. But you can make another cool observation using this fact. Consider any normal string where there is no question mark present. Can you now see that it is possible to create that string from ground up by starting from the first and the last character of that string and repeatedly inserting whatever is missing in between them? And that leads to our biggest conclusion yet, that is, only the first character and the last character are enough to determine the weight of a string. Now, if someone gave you this info at the start of this video, you might find it very easy to prove, but something that you might consider impossible for you to arrive at naturally if you are not experienced in these kind of problems. But I've just showed you a line of reasoning using which you can arrive at this observation yourself during the contest. But what if you are not smart enough to arrive at this observation? Would you not be able to solve this problem? That is not true, because even if you did not notice the fact of building the strings from ground up, even if you did manual case analysis, you would have eventually figured out that the non-terminal question mark does not matter, and that is enough to solve this problem. But what if the question mark is present at a terminal location? Since we already know that the weight of a string is decided by the first and the last character, the first player has full control of the game. If they want to lock it down to green, it will be forever locked down to green. If they want to lock it down to blue, it will be forever locked down to blue, no matter what the second player does with the non-terminal elements. So this is a winning position for the first player. They can do whatever they want with it. And of course the optimal move is to lock it down to blue and win immediately. So now we have almost solved the array version of the problem. That is, if both the terminal elements are already fixed, then there is nothing you can do to change the score. If one of the terminal elements is locked to be equal to green, you lock the other terminal to blue and your score will be 1 and you will win. But the last case that is remaining is, what if both the terminal positions are unlocked? What do you do then? In the last slide, we discussed that the position where one of the terminal elements is locked, suppose it is green, is always a winning position. Therefore, we cannot afford to give Bob that winning position. Therefore, our strategy should be to never ever lock the terminal element, because if you lock it down to green, Bob can also lock down the other terminal element to green and the score will be forever set to 0. But you also cannot skip your turn. So what is the next best thing that you could do? You can simply pass your time by picking any non-terminal element and doing random stuff on it, because you know that it will never influence the answer. But Bob is also smart enough to notice your move. If they notice that you are just passing your time by doing random stuff on this non-terminal element, they will also pass their time by doing some stuff on this non-terminal element. So this mirroring strategy is pretty common in game theory problems. So if you do some stuff over here, Bob can do the same thing here. If you do something here, Bob can do the same thing over here. If you do something here, Bob can mirror your move and do the same thing over here. Now you are in a position where the only position that are remaining are the terminal element. And now you are forced to lock down one of the terminal elements, and then Bob can win by locking down the other terminal elements to the color of his choice. But if the number of non-terminal elements was odd, then Bob cannot mirror your last move, and then Bob will be forced to lock down a terminal element, and then you can win by locking down the other terminal element. So now we have solved the array version of the problem as well. How do we solve the tree version of the problem? Notice that the terminal elements are the root and the leaves. So now suppose that the root is already locked down at the start of the game, and suppose it is green in color. Then your best strategy is to lock down all the leaves in color blue so that you can get a score of 1 along this path. However, Bob can also notice your strategy and they will try to destroy as many leaves as they can. So if there are L leaves that are unlocked, then you can lock L by 2 leaves in blue color, and every time Bob gets a chance, they will try to destroy L by 2 leaves. So now the answer is pretty clear when the root of the tree is locked down. But what about the case where the root is unlocked? That is, the root is green in color. Let us start with the simplest configuration where all the leaves are unlocked, they are red in color, and suppose there are a total of L different leaves. What is the maximum score that you can get? Of course, if you try to lock down the root in your first round, then as we discussed earlier, the maximum score that you can get is equal to L by 2 because Bob will now start the round. But what if you don't lock down the root in your first round? You might think that you have a better strategy of coloring a lot of leaves in green and finally coloring the root in blue to gain the maximum benefit. However, your opponent is smart enough to notice this strategy, and as soon as you have colored a good amount of leaves in green, they will immediately go to the root and color it to be blue or color it to be green, thus destroying your strategy. So you are also smart enough to notice that this is the way that your opponent is thinking. Therefore, nobody, like neither you nor your opponent, will risk creating a bunch of G's that are together. That is, if you create a green leaf, your opponent will immediately create a blue leaf to cancel out the effect. Therefore, it is clear that since both of you will follow this strategy, you will divide these L leaves equally amongst yourself. Therefore, nobody can really gain an advantage. But what if you already have an advantage at the start of the game? In that case, you should take that advantage, because if you are looking at the number of leaves that have not been assigned a color yet, you can never ever gain an advantage from your opponent. Therefore, simply count the number of green leaves and the number of blue leaves. If one of them is strictly greater than the other, you should lock down the root immediately, because you are getting an advantage. Because if you don't, then the opponent can lock down the root to his favorable color in the next round, because the opponent is smart enough to understand that on the unassigned leaf they can never gain an advantage. So because it will be distributed equally L by 2 and L by 2. So if they are getting even a slight advantage in the initial configuration, they will take it immediately. So the only case that is remaining is when there is no advantage in the initial configuration and the number of green leaves and the number of blue leaves is equal. In that case, in the previous slide, we have already discussed the optimal strategy, that is, nobody should risk creating a lot of greens or a lot of blues. Therefore, if you create a green leaf, your opponent will cancel it with a blue leaf. If you create a blue leaf, your opponent will cancel it with a green leaf. But what if the number of leaves is odd? So suppose you have 3 leaves. So if you create green, your opponent will cancel it with blue. But on the last leaf, if you turn it to green, then opponent will immediately go to root and color it with green and win this segment. Therefore, if the number of leaves is odd and there is no advantage at the start of the round, then whoever touches the last leaf loses. But do they really have to? Like, did you really have to touch that last leaf yourself? No, because you can waste your time on a non-terminal element, just like we did on the array case. So you simply go to a non-terminal element and waste your turn there. But the opponent can also mirror your move, right, as we discussed earlier. Therefore, if the number of non-terminal elements is odd, then the opponent will not be able to mirror your last move, and therefore they will have to be the one to touch either the leaf or the remaining root. So if they touch the root, you can simply go to the leaf and color it with your favorable color and win. If they touch the leaf, you can go to the root and color it with your favorable color and win. So this is exactly the same as the array case. This is the code for this problem. First of all, we figure out the color of all the leaves and the number of non-terminal question mark. Then if the root is already locked down to green or blue, we know that we should get the maximum number of leaves in the alternate color. So we do that over here. But if the root is not locked down and it is equal to a question mark, which is a red node, then we figure out if there is an advantage at the start of the game. If there is an advantage, then we can take the last leaf for ourselves. If there is no advantage, then of course we need to divide the leaves equally with our opponent. I will add the code, slides and some game theory problems in the pinned comments on YouTube. All the code that you have seen in this video will also be available on cfstep.com.